This is the Preparing for the ACT 2021-2022, the science passage number 5. If you know a particular question you want to find, go look in the description and click on that particular question to see that solution. So this passage says, over here on the left, as a sound wave travels through a medium, the wave becomes attenuated, that is, loses energy. And so the attenuation coefficient, so we've got this alpha, and for most people just treat it as a letter A, is the rate at which its intensity level, that is its volume, decreases. So it says figure 1 shows for 3 waves of different frequencies how A varies with temperature in 10% relative humidity. So that's going to be important because for figure 1, the entire time the relative humidity is 10%. Now that's different from figure 2, because here what they do is they show waves at 3 different frequencies, how A varies with relative humidity. So here the humidity is now different, and we're looking how that affects the alpha. Now what's kept constant here is the air temperature, 20 degrees Celsius. So anytime you have a graph, you want to know what the variables are. So here we've got relative humidity, and we've got the frequency, but then we also have the constant. Back over here in figure 1, our variables are temperature and frequency, but humidity is kept constant. All right, so question 28 says, what is the approximate maximum alpha shown in figure 1? So right off the bat, when they give us figure 1, they're telling us, all right, here's where you're looking. For a 200 hertz sound, all right, so that means we're looking at this sound wave in air temperature at 10% relative humidity. Well, we already said that it has a 10% relative humidity. We already know that. So this is kind of meant to, this right here in the problem is meant to mess you up. So the question is, what temperature does that maximum temperature occur? So we're looking at this type of line right here. So I'm going to look at that graph, and as I zoom in, here is the here's the maximum point right there. And it happens at about -5 degrees. So looking over on the right, we can eliminate letter G and letter J, but we have to ask, all right, what is the intensity? What is the alpha? Well, it's just above 3, or just on 3, so that's the reason why letter F is the correct answer. 29 directs us to look at figure 2. It says the attenuation coefficient for a 1,000 hertz sound. So it tells us we have a 1,000 hertz sound in the air at 20 degrees Celsius. Now we already know that that's a constant, so we don't have to worry about that. Reaches a minimum value at a relative humidity closest to which of the following? So we're looking at the solid graph, and we're asking, where is the minimum point? Well, let's consider our options. 25% would be right about there. 45 would be right about there. Then we have 65. And then we have 85. So of those 4, which one seems to be the lowest? It seems to be right around 45. That's where it seems to be the lowest on the graph. After that, the graph seems to be rising slowly, bit by bit. So number 30, for the range of temperatures and the range of humidity shown in figure 1 and figure 2, they're asking, is alpha for a 200 hertz sound wave more strongly affected by changes in temperature or by changes in relative humidity? Okay. So we're comparing changes in temperature or changes in humidity. And this is the difference. This right here is figure 1, and this right here is figure 2. So looking at these two graphs, we're looking at the 200 hertz sound. So we are looking at this graph right here, It goes up, it goes down right there. And then this graph right here, that is what we're looking at. So between those two, which one causes it to change more? Well, it is clearly temperature. That's causing this graph to change a lot more. With relative humidity, it's barely changing at all. So we know that H and J are wrong, but there are two answers where temperature is the right answer. So now we have to look into the reason. So it says the maximum variation in A, all right, and in the maximum variation in figure 1 and then in figure 2. So we have to look at this to say, all right, we already found the maximum. It's right up here, around 3. But where's the minimum? Well, the minimum is, let's see, way down here. And where is that? Well, that's somewhere about there, more or less. And so when we talk about variation, we're talking about what's the distance between the high point and the low point. That's about 2, give or take. Now, if we look over here on figure 2, the variation between the high and the low, it's barely anything. So the variation, the difference between the high and the low, should be bigger for figure 1. And that's what we have. It's 2.5 in figure 1, but 0.5 in figure 2. As opposed to answer F, where it says it's about 1/2 for figure 1 and 2.5 for figure 2, which is backwards. So question 31 asks, consider a 1,000 hertz sound in air at 10% relative humidity. At how many of the temperatures shown in figure 1 does alpha for this wave have a value of 18 decibels per kilometer? All right. Now the units here aren't that important. The key thing is the number. So we've got 10% humidity here, and let's see, where's 18? 18 is right there. So we're asking, all right, how many times does this graph have this amount? And so that's once, twice, 3 times, 4 times. So it happens 4 times that this graph, for this particular frequency, it has to be at 1,000 hertz, because that's what they give us, reaches 18 for alpha. 32. Here it says, suppose that we have 2 sound waves, 150 hertz and 1,100 hertz. All right, so we don't have either of those numbers. So 150 hertz is below all our available data, and 1,100 hertz is above all of our available data. So that's something to keep in mind. They're emitted from a speaker into air at 20 degrees Celsius at 45% humidity. All right, so figure 1 won't tell us anything because it's 10% relative humidity. So let's go over here. So we've got what we want. We've got 20 degrees Celsius, and we want 45% relative humidity. Well, that is right here. So it says, based on figure 2, as the waves travel away, the intensity level of which wave will more likely decrease at the greater rate. And so the key thing is that what's happening to alpha? Because alpha is the measurement of attenuation. Let's remind ourselves that word attenuation right there. That's over here. I can look up the word attenuate. It loses energy. And so oftentimes when we have those special words, go back to the directions and you'll see, all right, what's going on? So we only have 1,000, 5,000, and 200. So the question is, where is 1,100 likely to be? Somewhere out here. And where is 150 likely to be? Probably somewhere down here. So the question is, which will have the greater rate of decrease? And those two words often mess students up. Because, all right, greater decrease, a lot of students think, well, that means they want the lower number. That is, they want 150 hertz down here. But actually, we actually want the 1,100. Because it says the value of alpha is greater. And alpha, in this problem, in this scenario, alpha measures loss. Or rather, how fast you lose something. So the higher the alpha, the faster it's being lost. So that's why the answer is letter J. 1,100 hertz is higher up here, and so therefore it's going to be losing it faster. All right, 33. It says this graph shows for 3 different waves of frequencies. So here again, we've got our 1,000, our 500, and our 200 hertz. How alpha varies in the air with relative humidity at a particular temperature. Now notice they don't tell us. They just say a particular temperature. So the question is, based on figure 1, the particular air temperature is most likely which of the following? Now the key thing here is that down here we've got relative humidity, and it starts at 10%. And that's where this graph is, 10% relative humidity. Now why is that important? Well, as this graph goes on, the humidity goes up. But right here at 10, we've got information on that. Let's change color here. So this right here, 1,000 is at 14. Right here, 500 is at 9. Right here, 200 is at 3. So what we want to ask is, where does that happen on this graph? Where 1,000 is at 14, where 500 is at 9, and 200 is at 3. Well, we have some options. Is it negative 20 degrees? No. No, it's not. Because they're all the same. What about 0? So here's 3, here's about 9, there's about 14. What about 20? Here that's about 1, that's about 4, there's about 14. So that one doesn't work. And then 100, that's way over here. We've got about 1, 5, and about 18. So because for this problem, these numbers match up with these numbers here. Whoops. Undo that. That's why the answer is letter B. Thanks for watching, and check out all the other videos on this test.